AI-enabled applications on powerful cloud servers provide significant benefits, but offloading personal data raises privacy concerns. Splitting AI or ML models between the end user and the cloud ensures users can leverage cloud computing while protecting their privacy. Dynamic wireless channels due to mobility, jamming, interferences require careful decisions on splitting AI model to balance multiple factors. Trade-offs involve privacy protection, available transmission throughput, and device energy consumption. Dynamic real-time optimization is required in view of the changing radio conditions in real-world deployments. The topology consists of four main components: UE, running the head of the ML model; 5G base station, with an AI-based spectrum sensing system; application function, AF; and 5G core, responsible for selecting the optimal ML partitioning point; GPU server, hosting the remaining tail of the ML model. These are the key performance metrics being used in the throughput estimator. We also make use of IQ data from the front hall interface in UL slots to obtain a more comprehensive view of the channel conditions. The UL throughput estimator features a dual branch design, an LSTM and a CNN. The weighted outputs are then fed into a fully connected layer for final estimation. Table 2 compares our model with other approaches. The joint objective function is optimized by determining the optimal split point of the ML model between the edge and cloud, minimizing the weighted sum of E2E latency, privacy risk, and energy consumption. In the presence of interference, it achieves up to a 64% reduction in E2E delay. This is the GUI. It runs image processing on input image and outputs classification label and a confidence score. Now, let's dive into the demo. In our first scenario, under perfect wireless conditions, both systems perform similarly. Next, we introduce a jammer into the wireless environment. The running jamming spike can be observed at the spectrum analyzer on top right corner. Observe how the baseline system suffers from lower FPS and increased end-to-end delay, while the adaptive splitting system dynamically adjusts the partitioning point, maintaining better performance. The setup to emulate interference scenario of the edge UE between two neighboring cells is shown in the picture. In scenarios with UE to base station interference or base station to base station interference, the fixed splitting system struggles with similar challenges, reduced FPS and increased delay. The adaptive splitting system, however, adjusts in real time to mitigate these effects, ensuring optimal operation. We also set up another interference scenario between base station and base station due to different time slot configurations. By adjusting the optimization weights of privacy leakage, end-to-end delay, and UE energy consumption, the adaptive splitting system selects different splitting points, yielding varying impacts on real-time metrics. This flexibility highlights the adaptive splitting system's ability to tailor performance to specific requirements, making it highly versatile in diverse wireless conditions. By leveraging AI-based spectrum sensing and dynamic model partitioning, the system enhances privacy, reduces E2E latency based on available throughput, and extends UE battery life under varying wireless conditions.